In this video, we'll be exploring increasing and decreasing patterns. Patterns are extremely important to make sense of our world in a mathematical way. We'll use patterns to solve problems such as how many tables are needed to sit a certain number of people. Let's begin by exploring patterns in general. Here is a sequence of numbers. Do you think it's a pattern? How do you know? If you think it's a pattern, what would the next three numbers be? If a sequence of numbers is a pattern, then one should be able to extend the sequence. In other words, once a pattern has been identified, one can predict other numbers in the pattern. To figure out the next three numbers, let's look for what makes this a pattern. You may have noticed that to go from one number to the next, we add 4 each time. So to extend this pattern, we can keep adding 4. So the next number is 19, followed by 23 and 27. Now that we have our pattern, we can describe it by saying that it starts at 3 and goes up by 4 each time. Because this pattern is going up, it is called an increasing pattern. When we are able to generalize a pattern this way, it is called a pattern rule. We can then use a pattern rule to figure out later terms in the pattern. For example, how can you figure out what the 20th term in this pattern would be? One approach we could take is just to keep extending the pattern one number at a time. But this is a lot of work. So in grade 6, students learn to describe a pattern rule that makes finding any term much simpler to do. To see how we can come up with a more powerful pattern rule, let's start by noticing that the 7th number is 27. This resulted by starting at 3 and then adding 6 groups of 4. So to figure out the 20th number, we start at 3 and then we would need to add 4 19 times. Finishing this calculation leads to figuring out that the 20th number is 79. A helpful way we can represent a pattern is with a table of values. The input counts the number of terms in the pattern, and the output lists the actual numbers in the pattern. Because we will be relating output numbers to input values, this is called a relation. To work with relations, we are going to use something that is called an input-output machine as a way of seeing how input leads to output. For example, when 1 is the input, 3 is the output. When 20 is the input, 79 is the output. Our objective is to figure out the pattern rule that turns the input into the output. To figure out the pattern rule, let's look for relationships between the input and the output. We've noticed that every time the input increases by 1, the output increases by 4. We also noticed that we could turn the repeated addition of 4 into multiplying by 4. To complete the pattern rule, we need to figure out how to go from this middle column to the output values. You may notice that it is by subtracting 1. So our pattern rule is to multiply the input by 4, then subtract 1. In grade 6, students learn to use a variable to represent a number that can change. For example, we could use the letter n. Instead of writing n times 4, we usually write this as 4n. We use the term constant to represent this part of our rule because it is the same for every number in the pattern. Altogether, we call this an algebraic expression. We can see this rule play out with the input-output machines by having the first machine multiply the input by 4 and the second machine subtract 1. Let's try this with some input values. First, these numbers are multiplied by 4, and then 1 is subtracted. We could use one machine by making our expression simply 4n minus 1. How could you use this expression to figure out the 100th number in the pattern? We input 100 and multiply it by 4 to get 400, then subtract 1, and that gives us an output of 399. If we switch the order around, we still have a pattern, but it is called a decreasing pattern because the numbers are going down. Our expression would no longer apply. What do you think the new expression is? This time, we are subtracting 4 as we go from number to number, so we can represent this as subtracting 4n. We next need to figure out what the constant is. That is, what is the number we are subtracting from? There is an interesting way to figure out the constant for any of these relations, and that is to extend our pattern to the left, because then n would be 0. So our pattern rule is 27 minus 4n. We should check this out. By calculating with different input numbers, we see that it does fit the pattern. Next, we're going to look at a visual pattern. Visual patterns like this one are a nice way to visualize how a pattern is growing as a relation. You can find more patterns like this at visualpatterns.org. Looking at this pattern, what do you think comes next? Before we answer this question, let's use figure numbers to represent the input values of the relation. The question can now be rephrased as, what does figure 4 look like? To answer this, it helps to see how the pattern builds. We start at figure 1, then we add 3 cubes in this way to make figure 2, add 3 more cubes to make figure 3. So to make figure 4, we need to add 3 more cubes. Now that we see how this pattern grows, how could you figure out how many cubes are in figure 10? There are a number of ways to approach this question, but let's make a table of values with the figure number representing the input. The number of cubes will represent the output. To solve the problem, we need to figure out how many cubes are in figure 10. As the figure number goes up by 1, the number of cubes goes up by 3. So to go from figure 4 to figure 10 means going up by 6. So we would need to add 6 more groups of 3, or 18 more cubes. This leads to a total of 31. Let's generalize this pattern to look for the relation. In other words, how can we determine how many cubes there are given the figure number? Look carefully at the visual pattern and think about what stays the same and what changes. Next, consider the figure number of each one and try to see how this number shows itself in each figure. You may have noticed that the top column of cubes is the same as the figure number. We can also see the figure number of cubes branching off to the left and to the right. This is the part of each figure that changes according to the figure number. For example, in figure 3, we see 3 groups of 3. But then there is one more. Similarly, in the other figures, we see 3 groups of the figure number and then one more. The number of cubes for each figure is made of a part that changes and a part that stays the same. With this way of seeing the pattern, how could you predict how many cubes are in figure 50? Figure 50 would have 3 groups of 50 and then one more, and this leads to a total of 151. So we have a visual pattern which we can represent using a table of values. This middle column shows how the number of cubes relates to the figure number. What's left is to figure out an algebraic expression of the pattern rule. If we let our variable be n, then the number of cubes must be 3 times n plus 1, which we represent as 3n plus 1. Let's notice the connections between these three representations. We saw the 3n in the visual pattern by seeing 3 groups at the figure number. We saw the 3n in the table by noticing the number of cubes goes up by 3 for each figure number. We see the plus 1 in the visual pattern as a cube that stays the same from figure to figure. In the table, we use the plus 1 in our calculations. Notice we also see the 1, which is a constant, if we extend our table backwards to figure 0. We saw this before when we looked at the other relation. We name these three representations as visual, numerical, and symbolic. In grade 6, students also learn to represent patterns using a graph, and this is called a coordinate grid for reasons which we shall see. A graph is made up of axes. There's the horizontal axis and the vertical axis. We label each axis using the column names from a table of values. The axes are number lines and they start at 0, then go up from there. To plot a point on the graph, we take an input value, like 3, and pair it up with its output value, which in this case is 10. The numbers 3 and 10 come together to form what we call the coordinates of the point. And this is why it's called a coordinate grid. Another term we use is ordered pair, and it consists of the input and output values enclosed in brackets. We always place the input values of the relation horizontally and the output values vertically. In the same way, we can plot the rest of the points from the table. Because the points lie in a straight line, this is called a linear relation. And all of the relations students do, not just in grade 6, but also through grade 9 and most of grade 10, will be linear. We can now extend to the graph the earlier connections that we noticed between representations. The 3n shows how the pattern changes between two sets of values. We notice that same relationship in the graph. Note as well that we can see the same relationship between any 2 points as long as the change in output is 3 times the change in input. The one that we saw in the table corresponds to the one that we see as the point on the vertical axis. In general, the constant will always be the value on the vertical axis. So we now have 4 representations of patterns. And all of these representations have meaningful connections. So now let's apply what we have learned about patterns to solve some problems. Here we have an input-output machine, and the problem is to figure out an expression for the pattern rule. In order to do that, let's see what happens when we input these numbers. What can you figure out about the rule for this pattern? First, let's look for what changes. As the input goes up by 2, the output goes down by 4. This is equivalent to saying that as the input goes up by 1, the output goes down by 2 each time. So we know that the expression for a decreasing pattern, in this case, is 2n subtracted from some number, the constant. We saw before that the constant is the output for when the input is 0. Extending this pattern backwards, we see the number must be 20. Let's check this expression with one of the sets of values from the table. When the input is 6, we do 20 minus 2 times 6, which is 20 minus 12, and that equals 8. The expression is valid. For our next problem, let's look at this visual pattern. How many paw prints do you think there are in figure 42? We can see that the constant is 3 paws, and the other part has 2 groups of the figure number. So our rule is 2n plus 3. Applying this rule to figure 42, we can calculate that there are 87 paw prints. For our next problem, we'll return to what was mentioned at the beginning of the video. We need to figure out how many tables we need to sit 30 people. But first, we have to know how the tables and chairs are arranged. Now that you can see this arrangement, how could you figure out how many tables are needed for 30 chairs? There are many strategies we could use to solve this problem. One strategy is to begin with a table of values. And then we could graph the relation. We can use a straight line to extend the relation. We are looking for which point on this line corresponds with 30 chairs. This point shows that it will require 14 tables. Here's a different strategy we could have used. We know that we need 30 chairs. No matter how many tables we have, we'll always have these 2 chairs on the left and right sides. That means that we have 28 chairs left, and each table adds 2 more chairs. So we would need 14 more tables. This strategy corresponds to thinking of an expression for this relation, which happens to be 2n plus 2. Our final example is an open problem. If a pattern has the numbers 8 and 14 in it, what could the pattern be? Once you have chosen your pattern, what would the 20th number in this pattern be? Try to think of several different ones. One way we could create a pattern is to go up by 1s. Or you could go up by 2s or 3s. Perhaps your pattern starts from an earlier number. Or perhaps you made a decreasing pattern. Let's use this pattern to figure out the 20th number. Because it goes up by 3s, we know the expression of the pattern rule will have 3n in it. And if we extend to the left one number, we can see that the constant will be 2. Now that we have our expression, we replace n with 20 and calculate that the 20th number in the pattern is 62. This video addresses several learning standards in the Mathematics Grade 6 curriculum. Throughout the video, we explored and represented linear relations in various ways. Developing a pattern rule was key to generalizing our patterns. In this content standard, we focused on increasing and decreasing patterns represented by expressions, tables, and graphs. Functional relationships are what I referred to throughout the video as relations. As your child learns about patterns in their classroom, several curricular competencies may emerge. For example, we used expressions to model the table and chair relation, as well as with visual patterns. We made important connections between the different representations of patterns. And finally, we solved many of the problems using more than one strategy. With solving problems involving patterns, we can use tables, expressions, or graphs, or a combination of these. We hope that you found this video valuable in helping you support your child in their learning about increasing and decreasing patterns. Please check out the other titles in this series.